Alright, so welcome back to everyone. A very warm welcome to all of you, my dear students. A very warm welcome to all of you. So, guys, my name is Dr. Shankar Sir, and I'm your physics educator. So, guys, in this session, we are going to speak of the properties of the solids. Okay, so in this session, what we are going to do, we are going to talk about the chapter of properties of the solid. Okay, we will be talking about the properties of the solids. Okay, okay, wonderful. So, guys, in the last session, we have been speaking about the Hooke's law. Okay, so let me give you, you know, some sort of a revision to this. So, basically, first thing I told you about in the last session that in Hooke's law, it is basically valid till the limit of proportionality, valid till the limit of proportionality. Okay, first thing. Secondly, it says it is in three parts. It says that corresponding stress is proportional to corresponding strain. That means the normal stress is proportional to normal stress, strain, shear stress is proportional to shear strain, and the volumetric stress is proportional to the volumetric strain. Okay, and from here we could write, when we let go of the sign of the proportionality, it becomes modulus of elasticity times the normal strain or longitudinal strain. This will become g times gamma, and this will become volumetric strain will become k times epsilon v, that is volumetric strain. Okay, now, in this E was the Young's modulus, that is the modulus of rigidity, the modulus of elasticity, or we call it Young's modulus or Young's modulus. Okay. Then we have the G, that is modulus of rigidity, and or you can say it as shear modulus. Okay, then we have this K, which is what we call as the bulk modulus, which we call as a bulk modulus, right? So basically, these are what we call as the elastic constants. And see what is the relevance of these elastic constants. So basically, these are the properties associated with the materials. Okay, you will agree to this point that the different material behave differently when subjected to a similar force. When subjected to, my dear, a similar force. So when they are subjected to, when they are subjected to a similar force, when they are subjected to a similar force, they behave differently. That is what we call as the elastic behavior. Now, these elastic constants will somehow determine the behavior of different materials under a given type of loading condition or given type of load. Okay. Okay. Now, so we have been analyzing in the last session the first part of this equation, or the first part of the Hooke's law, which says stress is proportional to stress is proportional to normal strain. Now I'll be telling you how to use this formula and how what kind of a questions can come using this formula and the outcome. Then we'll move to the shear strain part. We are going to do like this. Okay. First, we are going to deal with the this part of the equation, and perhaps the most important one. Okay, so you will see a lot of question getting asked from this part of the Hooke's law. Okay, so now how we are going to deal with it. So I have given you in the last session also this thing. Let's suppose we are having a three-dimensional object, three-dimensional body like this. Okay, now when we are having this three-dimensional object, let me say that we are applying a force here. Okay, and when we talk about the properties of solid, basically we are seeing the equilibrium problems. The static equilibrium problem. Static equilibrium problem, what is the meaning of a static equilibrium problem? So the problems in which the net force acting on a body becomes zero. You take in any direction, right? That is, the sum of forces in x direction is going to be zero, right? sum of forces okay. uh, Forces are in equilibrium. That means if you consider the force in any direction, you may consider the forces in x direction, you may consider the forces in y direction, you may consider the moments on any body. Okay, so in whichever direction you see, in whichever direction you see, you are going to have the summation of all the moment is also sort of a force, right? That's all we have seen in the previous chapters, right? Okay, so when in such a condition a body is having to act, so the physics applied to the body is what we call as the, properties of the solid. That comes under this uh, category, or it is also known as mechanics of solid, right? It is also known as mechanics of solid. Now, let me tell you. Now, see, ultimately, what is our aim in the examination? What they are going to ask you? They are going to ask you questions. Right. Now let's try to understand. So in the last session, I have explained that what is the stress. Stress is basically internal resisting force per unit area. So within the limit of proportionality, that is under the zone of Hooke's law, you can write the internal resisting force also equal to the deforming force or the external force. So this is P upon area. Okay, so the stress when you are finding, you just need not to worry. You need to use the external force upon area. That's all. Right. Okay. The reason of it, I have told you in the last session that when an external force is applied on a body, every point on the body tries resisting that external force. Okay. Due to which a term comes up that is what we call as the what? The stress. That is the internal resisting force per unit area. So the stress is going to be P upon A. The stress is going to be the force upon the external force upon area, right? Now in this, remember what is the area. In this, remember what is the area that we are so force is P, obviously. Now what is the area that we are going to take here? What will be the area that we are going to take here? What will be that area that we are going to take here? So the area that we need to take here is the area that we need to take care is what? The area that we need to take care here is, so see, this is what we call as the perpendicular, okay, the normal stress. So we need to take the area which is normal to the force. So what is that area? So this is that area now. So can I write sigma is equal to P upon A? So A is B by B into D. Okay, this is going to be the normal area. Right, always when you are doing it like this, you always must take the normal area. Is it fine, madam? Please answer me. Yeah, yeah. Now let's suppose the force would have been applied like this. Let's suppose this is the body. This is the three-dimensional body. Or I'll make it on the next page. See which area to take and all this, which dimension to take. All this is very, very important, right? Okay. Now see. Come. Now please understand this. So here, let's suppose a force is acting P like this. Okay. And this end is fixed. One end could be fixed or the similar force can be applied. Okay. This is the force P and this is the fixed end. So the reaction will be P. The reaction will be P. Understood? Okay. Now this is going to be B, this is going to be D, and this is going to be L. Okay. Now, in this case, what is going to be the stress? Stress is going to be P upon BD, isn't it? It is going to be force upon BD. If I consider this as B, this as D, this as L, right? So always remember that what is the area that you are taking to finding out the normal stress, right? So sigma is equal to P upon BD. Now what is going to be, so this is stress is sorted. The stress is sorted, right? Now please understand this. So now from this, the other equation which says stress is, now see, stress is directly proportional to E times strain. So can we write it like this also? Strain is sigma upon E. So this is what, this is the normal strain, okay? Or we call it longitudinal strain, okay? Now longitudinal strain has nothing to do with the length, but actually it is the strain parallel to the direction of the force. The strain happen to be in the direction parallel to the direction of the force is what we call as the longitudinal strain. So Hooke's law relates the longitudinal stress and longitudinal strain, right? Okay, so what is going to be this longitudinal strain? So this is going to be delta by L sigma P by A into E. P by A into E. So delta will become PL upon A. Is that fine? Beta, please answer me. Bole. Give me a yes or no. Bole. Please give me a yes or no. Okay. Now this is the formula of the elongation that we are going to use, right? Now if you see the same body in two dimension, if we are going to see this body in two dimension, okay, L and this is P, okay, and let's suppose this is D, okay, like it can be a diameter or anything, right? Now in this case, what is going to be the stress? So let's suppose D is the diameter. Okay, so what is going to be the normal stress, sir? It is going to be force upon area. Area, which one? Always the normal one. So it is going to be sigma is equal to P upon pi by 4 D square, and delta is equal to PL upon AE. So which is the A here? That is pi by 4 D square into E, right? Because when it is going to be stretched, when this kind of a load is applied on it, it is going to be stretched somewhat like this. Understood? It is going to be the stretched somewhat like this. So this is the formula, or this is the expression for finding out the deflection of a body under the normal loading condition. That is when the load is applied normally to the cross section. Very, very simple. Now same thing can you do here also? Yes, sir. Now in this again delta will be PL upon A, right? PL upon A, right? It is like this or it is like that. So in this weight must also act now. So unless otherwise mentioned, you cannot take the self weight. See, obviously self weight is there in everybody. Okay, but in this chapter, what is the assumption that we are taking while writing all this Hooke's law, the formulas, everything? That the self weight is neglected. Remember. So unless they ask you to take the self weight, you are not considering it. This is the effect due to the externally applied load. Okay, which is also known as the axial load. Okay, I hope it is fine to everyone. Right. Now I want to ask you, the live students. So guys, if a load is applied on a body like this, like normally or perpendicularly to a cross section, will you be able to get the normal stress and the longitudinal strain and the elongation or the deformation? Is it fine? This is the only formula that we have. Very simple, sir. Yes, we'll definitely be able to do that. No problem at all. Isn't it? Very simple formula, right? And remember, we only have this formula to be used. Okay. Now, what is the sign convention we'll be taking up? So, sign convention we'll be following, or what is the sign we are going to take? So, we are going to take tensile load as positive, okay, and compressive load as negative, tensile load as positive, and compressive load as negative. And for elongation, in the same thing, elongation that is positive, okay, contraction that is negative, right? Understood? Okay, so this is the sign convention that we are taking along. Okay, now see, when we are talking about the body, so basically this is related with the strength of the body. See, whenever we are designing any body, let's suppose you are sitting on a chair. Okay, I'm assuming that when you are watching the sessions, you are sitting on a chair, right? Now let's suppose you are sitting on a chair. Now, if you sit on the chair and the chair breaks, that is not a good thing to happen, right? So basically, this context of physics is utilized in designing the component, right? Designing means for a given load, you can get the dimension, okay? Like you want to have any particular component working under given conditions, right? Okay, so if you have the load, you may calculate the dimension using this all this thing. Or when you have the dimension, you can tell that under this dimension, this material, what is the maximum load that can be undertaken by a particular body. So for that, you need to know some strength part. Okay, some strength. So there are two type of strength that we normally speak of. One is the yield strength, that is the SYT, we'll call it, and there is ultimate strength. Okay, I'll be telling all of it through the stress strain curve. So ultimate strength is going to be SUT. Ultimate strength is going to be SUT. Okay, so this is like for example, for mild steel, if I quote, so for mild steel, it is nearly 250 megapascal, and this is 400 megapascal. Okay. So what is the simple meaning of this yield strength and the ultimate strength? The simplified meaning is that when the stress due to the external applied load in the body reaches the value of yield strength, there will be permanent deformation, right? And when the load acting on the body reaches the ultimate strength, there will be breaking. Actually, there will be neck formation, nearly break. Okay, within few seconds after the neck formation takes place, you will have the breaking of that component. Okay, yeah, okay. So if a component is going to reach the the load is applied on the body. Just one minute. Yeah, sorry for some technical issues. Sometimes it happens, right? So now please tell me that what is the yield strength? So when a load is applied on a body, stress comes up. If that stress increases the yield strength mark, it is going to be have permanent deformation. Okay, so this is the point corresponding to the permanent deformation. This is the point corresponding to the permanent deformation. Okay, so basically the stress in a body when increases the yield strength mark, it will have the permanent deformation. And ultimate strength, at ultimate strength, that means if the body reaches this mark of ultimate strength, it is going to be break. Okay, it will have a breaking in it. Okay, it will break down, right? Okay, so whenever you are deciding the dimension of any component or for a given component, see, this is the bottom line. See, this is a common knowledge, no? Like, please understand this. So, see, everybody knows this, right? Those who are not learning the physics also are knowing it. See, very basic concept I'm going to tell you now. I'll just give you one example. See, I am a person of, if you see me really, like in front, I am a 6 feet 2 inch person, okay, having a weight of nearly 110 kg, right? Now, if you come with me, okay, and wherever in your city you must have gone to places, markets, and all, so you might have observed that there are shops which are selling the chairs for small kids also. A very small chair, right? Cute chairs are there. Now, if I go with you and if I try sitting on those chairs, what will happen? The shop owner will come and he definitely throws me out of the shop, isn't he? Right? Why? Because he also knows that if on a body the load acting is more than its capacity, right? The body is not going to sustain and it is going to fail, right? Now, what we need to do here, so we need to ensure that our body don't get failed under any circumstance, right? Under any circumstance. So there can be you can be given as the strength, or sometimes they use the word like the permissible stress, right? So see, we are not going into much depth into it, but permissible stress is somewhat failure strength. Failure strength. Why I am writing failure strength? So from failure strength, I mean it can be yield strength also. It can be ultimate strength also upon factor of safety. Upon factor of safety. Are you getting my point, Bra? Okay. Sometimes they use this word allowable stress. Okay, as the name suggests, allowable stress. So if you buy, you buy any component in this world, okay, any standard engineering component, you will see that in every component it is written that this component may bear this much load, right? Anywhere that you see, you travel to the railway, you purchase a car, on a bike also, okay, like maximum this much load can be applied. Even the machines which are used to measure the weight also, their maximum capacity is mentioned, okay. So see, permissible stress, allowable stress, what is FOS? It is actually factor of safety. So since when we are doing all these things, we are taking some assumptions, right? Right. Like normally when we deal with the Hooke's law, we consider the material to be isotropic. That means that the properties of the elastic properties of the material do not change with respect to the direction. Okay. We neglect the self weight. So all these what we are considering, due to that reason, we come up with this term permissible stress or allowable stress. I hope it is fine to everyone. Right? Okay. 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 So now what is the aim of the chapter basically? So here we are supposed to design a component, right? We need to tell the dimension of the component, or we need to know for a given dimension the load on the component. So let's try once. Okay, you will see a lot of questions like this. So let's try to converge this concept in our mind. Okay. The aim is that a body should not be fail under the action of any given load. Okay, and there are two things. One is the stress, one is the deflection. Okay, okay. So ultimately, what is to be taken care of? So if on a body a force is applied, if on a body a force is applied, it can be like this or it can be any force. So when the force is applied, so the stress coming due to this force, that is force upon area. Now you know what is the force, what is the area that you must take, what is the area that you must be taking, right? And secondly, this is should be less than or equal to the permissible or the allowable stress. You must ensure that your stress is not increasing the allowable stress. The stress coming on your body must not increase the permissible or allowable stress or the strength of the body. Right? Okay. Now delta induced, this is going to be less than delta permissible. Okay, because two terms are very important. One is the elongation and other is the stress. Right? Now let us try one question to understand this concept completely. See, reading the equation is very important. Let's try this one. Very interesting question. The live students, I need you to answer the question. Come on. Let's do it. Let's take some time and let's try to do it. Please go for it. So in this question, you are given with the permissible stress and permissible elongation. Okay. Let's try to understand the question. So in this question, you are given with a load. So there is a body on which 10 kilonewton load is applied. It is having some diameter. Okay. And the minimum diameter is that we have to find. See, when we are making something, when we are manufacturing something, what we need to know first. So, sir, we need to know that what is going to be the dimension, then only we can manufacture it. Okay. Now, what is the purpose of this thing, studying this thing in physics? See, in physics, whatever you are studying in one way or another, it is, as I said initially, that all these laws are made. Okay, they basically trying to understand some physical phenomena and then they manipulate it. So this is the basic. That is why we are living in the world which is full of new age wonders, right? Right, the in the building that you are right now sitting, that is designed using this criteria only. Sir, how you know? Arey, I'm an engineer only, na? I have done MTech PhD from IIT Roorkee, right? So in engineering, mechanical engineering, civil engineering, this is of high use case. Okay, it is like, see, these kind of things we engineer do like this. Okay, like the bond beta we have now. So in the milk, we put this mechanics of solid and then we drink it. Are you getting my point? So this is having a very high use case, and this is the very basic of that. Okay, so whenever you are designing anything for that matter, car, train, bullet train, aeroplane, building, right? Anything, bridge, spillways, anything, anything, even the chair you are sitting at, the bed you are sleeping, the school you are going, the bench you are sitting, everything is somehow related to this thing. Are you getting my point? Right? Okay, wonderful. Now, in this, what we are trying to get, okay, so we want to make a circular body, we want to make a circular bar. Now, on that circular bar or that circular body, the load applied is 10 kilonewton. So, when the load applied is 10 kilonewton, Okay, we want to determine, or we want to find out that what should be the diameter, so that it do not fail under this loading, right? And to design it to get you the diameter, you are given with some information that the permissible stress is 100 megapascal and the permitted elongation is 1 mm. Now, what is the meaning of this, permitted elongation or permitted stress? So simply it means that, if the stress coming in this body exceeds this point, or the load coming in this body, or the elongation in this body due to this load, if exceeds 1 mm, if exceeds 1 mm, if exceeds 1 mm, okay, what will be the diameter? Please answer me. Please try it. Please try it. I'm very sure we can do. Please do. Please try. The live student. Please get me the minimum diameter required so that this component will be saved. Okay. What is the safe condition? At of what minimum diameter I must make this body so that it comes under this condition that permissible stress is 100 and permissible elongation is 1 mm. Can you please try it? I'm very sure we can do it. Please go for it. See, we have only one formula, right? This, sir, we have a self-weight case. We have seen another formula. It's only this formula. Don't worry about it. We'll do with this formula. Please do it. See, if you try to do, definitely it will solve. See, these kind of thing, what I suggest you that you try to understand that what formula has to say. Okay. If at all you learn this thing that what is the formula is saying, you will be able to do a lot of things, right? You will be able to deal with a lot of things, right? Please try to think in that way. Okay. Okay. Now, now. So, any live students who would like to answer me this? Any live student? Would you like to give me answer of this? Anyone? Anyone who would like to answer me? See, trying is very important. That is why I am giving you some time. Those who are, watching the recorded session, I suggest that you also try these questions beforehand. Sir, if this question will come in the NEET, see, from this question you will be able to understand the concept very well. And once the concept is understood, whatever is coming in NEET or in JEE or in any paper, that doesn't matter. Okay. See, I have seen many people teaching this. See, I normally don't comment like this, but see, I am an engineer, right? And when I am teaching you this and fluid and thermal, so see, I can give you some shortcuts. I give you some easy ways to solve it. It's not much complicated, right? Like for example, I am going to give you a way uh, of loading diagram, right? From that way you will be able to understand the or solve many problems very easily. Okay, but for that you have to do some try. Unless you try, you will not be able to understand the concept. Please go for it. Please go for it. Please try. The live students, see, without you trying it is not going to work. So I'll do. Now see what you have to do. Okay. Now this is a normal load acting perpendicular to the cross section. Okay. Now under this kind of a load, what is the stress that is coming in the body? Stress induced, that means the stress induced or stress comes due to this load. Okay. Now what is the stress due to this load? So what is the stress? Sir? Stress is force upon area. That means 10 into 10 to the power 3 upon area. Area is pi by 4 d square. Pi by 4 d square. And this must be, first of all, less than equal to the permissible stress. Okay, so this will become 10 into 10 to the power 3 divided by pi by 4 d square. Sigma permissible is 100. Okay, now from here, if you calculate this d, you will be getting somewhere near 11.27 mm. Okay, when you calculate it, you are going to get somewhere near 11.27 mm, right? Okay, and you need to take care of the units also. See, units also. So I hope you know the units, megapascal, pascal, and everything, right? Do you? Okay. See, if you want to take care of the units, so see, 1 megapascal is 1 Newton per mm square. So right away you can write 1 megapascal is 10 to the power 6 Newton per meter square, and 1 meter is 1000 mm. So this will become 1 megapascal will become 1 Newton per mm square. Okay, so the diameter will become 11.27 mm. Is that clear? Please answer me. Right. So we got the answer. The diameter is 11.27 mm. So no, sir, this is not the answer. Or if it is the answer or not, we can't comment on it. Right? Why, sir, we cannot comment? Because see, you have found some solution from one given, data, one given condition. Okay, but you have one more condition. First condition that must be satisfied is that the permissible stress that is on the body, the permissible stress on the body is the permissible stress on the body is 100 megapascal. Now, under this load, you, if you do not want, see, what is the meaning of this equation? The meaning of this equation is that the stress will be less than 100 megapascal or the permissible stress only if you produce or if you design a component having diameter equal to 11.27 or more than 11.27 mm, right? So if the diameter is more than 11.27 mm, that basically means is that the stress that is going to come in your body is well within 100 megapascal, so your body is going to be safe. Okay, your body is safe, right? But we cannot answer at this condition. Okay, now sometimes we urge to somewhat answering the question right away when we have some value, but it is not the case here. Okay, you have to wait for answering. Why, sir, we have to wait for answering? Because we need to check also. We need to check also that what is going to be, what is going to be, what is going to be this thing. Okay, right? So we cannot answer, but we interpret this equation that diameter should be more than or equal to 11.27 mm if in order to for you to remain safe and remain within this given condition of 100 megapascal. But we cannot answer because we have one more criteria to fulfill, that is the delta permissible. So what is the delta permissible? So what is this condition? The elongation coming in the body must be less than equal to the permissible elongation. So it must be PL upon A and less than equal to the permissible deformation. So what is going to be the P? P is 10 kilonewton, that is 10 into 10 to the power 3. What is this L? L is going to be how much? L is given as 1 meter, so it is 1000 mm. See, when you're, I either see you can choose to put everything in meter or in mm. I prefer the mm because sometimes if they are asking you the answer in mm, right? Okay, so when they are asking you the answer in mm, it is always advisable because see, when you change it into meter, you are playing in decimal. So sometimes some units get rounded off. Are you getting my point? Okay, although it hardly matters, but see, whichever way you prefer, I prefer go with the mm. So some zeros are already sorted out. Right now, what is the A? Sir, it is pi by 4 d square. Sir, how without calculator we are going to do this calculation? Don't worry, I am giving you this question for the understanding of the concept. That is the idea, right? Okay, that is the idea. So this is going to be delta permissible is going to be 1 mm, right? It is 1 mm. Now from here, can we calculate the D? So D will become greater than equal to, so when you calculating from it, you are getting D is greater than equal to 7.9 mm. How much? So we are getting it equal to greater than equal to 7.9 mm. Okay. Now from this criteria or from this condition, what you are getting? You are getting that you must have the diameter of this body more than or equal to 7.9 mm, right? And what is asked in the question, sir? Minimum diameter. So what shall be the final answer? What shall be the final answer? See, you had two conditions. One was this, that whatever stress is coming in the body, okay, shall be less than equal to the allowable stress or the permissible stress. And the second condition is this, elongation coming in the body shall be less than equal to the permissible elongation. Now from here you are getting this very relation that D is 11.27 mm greater than equal to, and from here you are getting greater than equal to 7.9 mm. So now they are asking you the minimum diameter. So what shall be your answer? Can any live student please answer me? Right, what shall be the minimum diameter? In the case, see, we are to find the diameter, the D of this particular component. So we are asked about the minimum diameter, right? And that is only the thing makes sense now, isn't it? Will they ask you the maximum diameter? You are making a chair, what could be the maximum, dimension of that chair? It maximum could be anything, no? Right? For a given load, maximum could be anything. It always, see, when you are calculating the dimensions, it is always you are calculating by default minimum possible dimension, right? Because somebody has to make it also. The higher, higher the dimensions, higher the diameter, higher will be the costing, and you always want to reduce the cost, right? Do we like to pay money? No, sir. We like to take money or save money. We don't like to pay money, right? Isn't it? Like in an academy, you don't have to get lot of content. You don't have to pay anything, right? Free education, isn't it? You come to our platform, right? All the special classes are free for you. Not a single penny is to be paid, right? And so many concepts that we can learn. So, what is the minimum diameter? From one sort of calculation that you did, you are getting 11.27, and from one calculation, you are getting 7.9 mm. So, what is going to be the minimum diameter? Can you answer it? Can you answer it, beta? Bully. Anyone? Anyone? Now, see, when I ask this, many of you who would be, watching this, all of a sudden must be thinking, what you are saying, sir, 11.27, 7.9. So minimum diameter is 7.9. So no, the minimum diameter is 11.27 mm. That is going to be your answer. Or is it, how is possible? They are asking us minimum diameter, you are telling us maximum diameter. So see, please try to read the equation. Okay. See, that is what I am trying to infuse into you. So this is basically the safe condition in this particular condition or criteria, and this is the safe condition in this criteria, right? So what is the safe condition in the first? So it says if the diameter is greater than, if diameter is more than 11.27, then only you will be safe. So if at all, if you answer 7.9, 7.9 is very well below 11.27, isn't it? 7.9 is very, very below 11.27. Do you agree or not? So if you answer 7.27, you are going to get failed here. You are going to get failed in D. Understood? You are going to get failed in D. Are you getting my point, my dear? Right? Okay, so don't do that. Don't do that. Right? Please read the equation. Please understand what equation has to say. Right? The first equation saying that you want to be safe, the diameter should be greater than 11.27. Right? The second condition says that if you want to be safe, the diameter should be more than 7.9 mm. So, what should be the final answer? It should be 11.27, because when you are answering 11.27, you are saving both the condition. Understood? So the answer is 11.27. So they many times to confuse you, they say minimum diameter, but you have to give, whenever you are calculating the dimension, you have to give the maximum out of the two values, or they may give you one more condition, like under this condition. Okay. So whatever conditions are there, and if you can find the diameter, or for example any dimension, then what you have to do, you have to basically choose the maximum one in order to be saved, or in order to be satisfying all the conditions, right? Now let's try this one. Please go for it. पिंटू राय, हेलो, नमस्ते, कैसे हैं आप? सॉरी, कुछ टेक्निकल इशू हुआ था, इसके लिए मेरा वीडियो ऑडियो बंद हो गया था, मुझे पता नहीं चला। तो बेटा हम बात कर रहे हैं प्रॉपर्टीज ऑफ सॉलिड की। कैन यू हियर मी? आई एम रियली सॉरी। So we have to do this question, all right? So we just have done this question, guys. Okay, we are trying, what we are trying to understand, we are trying to understand the use of these two very important formulas, right? Which comes from the Hooke's law, right? So in this order we have done this one question in which the load was given, we have to find the diameter, and now in this question you see the diameter is given. So as I said, this context of physics, okay, what is the use of this particular part of physics? So it basically helps us to find out what should be a dimension of a product, a component for a given loading, or when we have a dimension given with us, what could be the maximum load that can be applied or that can be sustained by that component. Okay, please try it. I'm very sure we can do it. Please go for it. That's right, I'm very sure we can do it. Please do it. Please do. Please try, guys. Pintu and all the other students. Please try it. Please try it. I'm very sure we can do it. Please go for it. The live students, please respond. Please do it. see how we can try this question, how we can do this question. So we have Young's modulus, we have permissible stress, we have permissible elongation. Find the maximum value of load P. So now again, see in this case, so please try to understand the use case of this concept. Right? In the previous one, what we did, we were given with the load and we found the diameter. That is the dimension. Now in this case, the dimension is given. In this case, the dimension is due. Now, when the dimension is there, we want to know that what is the maximum load. Okay, see how it is going to happen. So we have E, we have sigma permissible, we have delta permissible. Now we have to find the maximum value of P. So again applying this, so the sigma induced is less than equal to sigma permissible. Okay, so sigma induced is equal to force upon area, that is pi by 4 d square, and sigma permissible is 100 megapascal. Okay, 100 megapascal. So P upon pi by 4, that is 20 square, is less than equal to 100. So from here, when I calculate the P, I am getting 31.4 kilonewton. I am getting 31.4 kilonewton, right? Okay, okay. Now, what does this equation trying to tell you? Okay. Now, if you want this component, now please listen to me carefully. If you want this component to be saved in this condition where the maximum permissible stress is 100 megapascal and maximum permissible deformation or deflection is 1 mm. Okay, so you want to come up with P satisfying these two things. Okay, satisfying these two things. Now for that, you have done with the one condition. And now it says that P is less than equal to 31.4 kilonewton. Now what does that mean? So it means basically that if you want your component to be saved under this condition of allowable stress of 100 megapascal, your load must not be more than 31.4 kilonewton. If it goes more than 31.4 kilonewton, you will be failed. But can we answer this time? With this much information, can we give the answer? No, sir. We cannot answer the question right now. Why we cannot answer the question right now? So we cannot answer the question right now because see, we just have satisfied one condition. Okay, we have one more condition to satisfy. We have one more condition to take care of. Now let's come with the other condition. So it says delta induced is less than equal to delta permissible. So delta induces PL upon AE and delta permissible is 1 mm. So what is P? P is what? P is we have to find the P. L is 1 meter, that is 1000. Area is pi by 4 into 20 square, and Young's modulus is E, that is 200 into 10 to the power 3. 200 into 10 to the power 3, and that is less than equal to 1. So from here, when I calculate the P, I am getting somewhere near 62.8 kilonewton. Are you getting my point, beta? So again, the same thing happened. We had two conditions. One is sigma induced is less than equal to sigma permissible. Right, so the load must be satisfying this condition. Similarly, we have another condition, delta induced is less than equal to delta permissible. Now, from the first case, we are getting P is less than equal to 31.4 kilonewton, and here the P is less than equal to 62.8 kilonewton. Less than equal to 62.8 kilonewton. Now, in these two conditions, what shall be your maximum load? In the question, what they are asking you for? So they are asking for the maximum load. They are asking for what? They are asking for the maximum load. So what shall be the maximum load? See, in the question, they are asking maximum value of P. Now, what shall be the maximum value of P, guys? What shall be the maximum value of P? So, what you must say? So, you must say, sir, the maximum value of P. The maximum value of P. Now, many of you must be thinking, sir, it must be 62.8. We have one value that is 31.4, one value that is 62.8. So the solution or the maximum load should be 62.8, but this is otherwise. What should be the maximum load, guys? It should be 31.4 kilonewton. Are you getting my point, beta? It should be 31.4 kilonewton, and that is your answer. How come, sir? How come? Now, please read this equation. It says, the first one says that for you to be saved under this loading and these conditions of the stress and the elongation, or I may say, firstly, the stress. Okay, so what should be the first condition read? P is less than equal to 31.4. P being less than equal to 31.4, that means that the load, if you want to be saved, the load must be less than equal to 31.4. What does that signify? So if load is more than 31.4, then you are going to get failed in condition 1, right? Now, if at all the answer we give is 62.8, if at all the answer we give is 62.8, which is well above 31.4. Now, if the answer we give is 62.8, do you realize that we are going to get failed in the first condition? Yes, sir, absolutely. Right. But if we answer 31.4, it is well within 62.8. Okay. So when we answer 31.4, both first and second conditions are getting satisfied. Both of the conditions are satisfied. So the maximum load shall be in this case is 31.4. Okay. Okay. I hope you understood this. So see guys, how we are going to use these two equations. I hope that this is very clear to you. This is very much clear to you. Right? Now, let's come to one more thing. Okay? Let's come to one more thing. Now, see, please understand this very, very carefully. Now, have we observed something? So, what do you want us to observe? Have you observed something? So, or if you haven't done it yet, you can go ahead, do it today. If you like, there is a elastic. Okay, there is a elastic. Now, when there is a elastic, you are pulling it. What you are doing, you are pulling it, right? Okay, let's suppose we are having like this, somewhat like this. Okay, in two dimension we are observing first. Then we can have it interpreted in the three dimension also if we want to. Now let's suppose that this is the body. I'll just use firstly this one. Okay. On this body, the load is applied like this. On this body, the load being applied like this. Okay. The load is applied like this. Now, due to this load, do you realize that this is going to get stretched? This is going to get stretched like this. So, if this is L, let's suppose this is going to get stretched and this will be L plus delta L, isn't it? Let's say this is L plus delta L because the length is increased, right? Just one moment. It goes out of the screen. Just give me a moment. Huh? Oh my goodness. Sure. Sometimes while teaching, I forget the limit of the screen. Come, I'll just use like this. Okay, so our force is there. Let's suppose this is P and this is also P. Now I hope all of us realize this, that this body is going to have a stretch like this. This is going to be like this. It will change in, it will increase, that length will increase. It will see some increase of the length. Okay. This will going to be L plus delta L if the initial length was L. Okay. Okay, so this delta L we have seen now that this delta is coming from delta upon L, that is your longitudinal strain. That is what we call it as longitudinal strain. Longitudinal strain. Right. Now, can you observe here one thing for me? What, sir, you want us to observe? Now, if you see a load is applied like this, the load is applied like this, the length of this body is increasing. Okay. When the length of this body is increasing, can you feel one more thing? That is cross-sectional dimensions are decreasing. Normally, if you stretch a elastic, if you somewhat pull a elastic, when a elastic is pulled, okay, its cross-section dimension reduces like that. Isn't it? It happens or not? When you are pulling something, its length is going to get increased, but its cross-section dimensions are going to get decreased. Its cross-section dimensions will be decreasing. Understood, Vida? Okay. Do you agree to it? It happens or not? Yes, sir. Now see what is happening here. What is happening here? See, if I say that this dimension is d, if I say this dimension is d, you will see that in this diameter there is some decrease of dimension. So it will become d minus delta d. It will become d minus delta d. Yes or no? Please answer me. Do you agree to it? Yes, sir. So when length is increased, its cross-section dimension, that is diameter, decreases. Okay. And here comes a term that is the lateral strain. And it will be delta d by d. It will be delta d by d. And this is your lateral strain. This is your lateral strain. Right? In this case, this is going to be your lateral strain. Lateral strain means that the strain happens to be in the direction perpendicular to the direction of force. Okay. Now, in this force seems to be applied in x direction. The force seems to be applied in x direction. Okay. Due to which there is certain increase of the length. Right. But along with it, there are lateral strain also, because we can clearly see that its cross section dimension, that is the diameter, is decreasing or is decreased, right? Right. So here comes, point. And now similarly, you can observe here also. See, if a body again, see, 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 physics is all about the observations. Okay. Physics is more about the observation, that how you observe the thing. So see, on this body, this force is applying like this. Now, due to this force, do you realize that this is going to have a contraction in the direction of load, or if we are compressing it? This is what we call as the compression. We are compressing it. We are putting forces like this. So when we are putting forces like this, basically the length is now going to get decreased. Okay. Now when the length is going to get decreased, what you can see here. So length is decreasing. So this will become L minus delta L, isn't it? Okay, the length is decreasing. Okay, now what about the cross section dimension? So now you will see that the cross section dimension is increasing. So length is decreasing. This is L minus delta L now, because the load is compressive. And you see now this is increasing. This is increasing. That is d plus delta d, isn't it? That is d plus delta d, right? And again, the longitudinal strain and the lateral strain remain the same in this condition, isn't it? This is how we see now. When we compress something, its length decreases, but its cross section dimension, its width, its depth, or its diameter increases somewhat, isn't it? Okay. Now, do you observe that in the longitudinal strain and lateral strain, there is an opposite relationship? What is that opposite relationship, sir? If the longitudinal strain is positive, if the longitudinal strain is increasing, it's positive. The lateral strain is the decreasing of, isn't it? Right? See, length is increasing, but diameter is decreasing. In case 2, diameter is increasing, so length is decreasing. Right? Okay. So, see, understand this. This is what we call as the Poisson effect or the Poisson ratio. Okay. So, this Poisson effect, what Poisson he has given us. Okay. So, this is the Poisson effect. So, see, so when we talk about in 3D, longitudinal strain, every longitudinal strain is accompanied with two lateral strains, because when we see in 3D, there are three directions. So there will be one direction in which the load is applied. So the remaining two direction will be lateral directions. So every longitudinal strain is accompanied with two lateral strains. every longitudinal strain is accompanied with two lateral strains, but in opposite direction. But in opposite direction. That means if the longitudinal strain is positive, the lateral strain is negative, or vice versa. Like in this case, in the second case, the longitudinal strain is negative because it is contraction. The lateral strain is increasing, that is positive, that is elongation. Understood? So Poisson effect says that every longitudinal strain is accompanied with two lateral strains, but in opposite direction. But in opposite direction. Understood? Understood? Is it fine? Yeah. So every longitudinal strain is accompanied with two lateral strains, but in opposite direction. Okay. Okay. Because see, if longitudinal strain is positive, lateral is negative, and vice versa. If longitudinal is negative, the lateral is positive. And this is what we see regularly. If we pull something, its length will be increased, its cross section dimension are going to get decreased. Okay. Okay. If the length is decreased, its cross section dimension is going to get increased. Right? Sorted? Yeah. Wonderful. So we have this Poisson effect, and in 3D, see how to understand this. So if I see in three dimensions, see, let me suppose that we are having a body like this. See, understanding all these basic concepts will give you the confidence. Okay, so let's suppose in this case the P is applied here. Okay, like this. Okay, and this is L, this is B, and this is D. This is D. So what is going to be the longitudinal strain? So for longitudinal strain, I don't use any subscript. For lateral, I use the subscript L. So this will become, sir, delta L by L. This will become delta L by L, right? Then what will be the lateral strain, sir? Lateral strain will be delta B by B, and it will be delta D by D. I hope it is fine to everyone, right? Now on the same body, if the force is applied like this, see, and here I am assuming that L, B, and D are not very different from each other. Okay, it is like 100, 50, 700, right? Like that. Because if they are very different, like for suppose length is 1000 mm and B and D are 30, 40 mm, like that. Okay, then it will become the tendency of the load or the effect of that load on that body will change. Then it will become shear. Are you getting my point? It will cause shear. Okay. It will cause shear. Now see, this is the load P and this is length L, this is B, this is D. This is B, this is D. Right? Okay. Now in this condition, what is going to happen? I want to ask you that what will you write in longitudinal strain? What will be the lateral strain? Can you answer me? What will be the longitudinal strain? What will be the lateral strain? Please answer. All of you. What will be the longitudinal? What will be the lateral? Very good evening, Shiva. How are you doing, my dear? So, beta, my name is Dr. Shankar Tripathi. Okay. मेरा नाम Dr. Shankar Tripathi है. Welcome to the session. And it seems to me that you are coming to my session the very first time, right? So these are a brief credentials of mine. Okay. So B is the width, my dear. We are talking about the properties of solid. And right now I'm trying to explain the Poisson effect. Okay. B is the width of this. So I have taken a three-dimensional body which is having the length L, width B, and depth D. And I am applying the load like this P. Right? This is a body, I'm pulling it like this. Okay. Now I ask that in this case, what will you see as the longitudinal strain and what you call as the lateral strain? Can you answer it? What will be the longitudinal strain and what will be the lateral strain? Can you try answering it? Yeah. See, we are trying to discuss the, we are trying to discuss this thing of the poison effect. Now, many students have this misconception that the longitudinal strain is the strain in the limb. Longitudinal strain is not the strain in the limb. Okay, see how it is. Now, please understand this. So, this is epsilon. This is epsilon. So, this is going to be delta d by dt in this case. The longitudinal strain is the strain happens to be longitudinal strain is the strain happens to be in the direction parallel to that of the loading, and lateral strain is the strain in the dimension which are perpendicular to the direction of the load. So what is the lateral strain in this case? So it is going to be delta B by B, and it is going to be delta L by L. Understood, beta? Right? Okay, so lateral longitudinal depends upon the direction of loading. That is what I wanted to convey. Now, what is the Poisson ratio? A very important and very famous elastic constant is the Poisson ratio, and this is what we call as the mu. This is what we call as the mu. So my mu is not that good. You make the mu correctly. So what is the Poisson ratio? So basically, see, again, this is the elastic property of any material. Okay, like E, G, K. Okay, like E, G, and K. It is the elastic property of the material, right? Elastic property of the material. Okay, so what is the Poisson ratio? So Poisson ratio is defined as the ratio of the lateral strain, okay, the ratio of lateral strain to longitudinal strain, lateral strain to longitudinal strain with a minus sign, lateral strain to longitudinal strain, lateral strain to longitudinal strain with a minus sign, right? Why this minus sign is there? What is this minus sign is there for? So this minus sign is there because the lateral and longitudinal strains are having opposite tendency. Okay, if longitudinal strain is positive, lateral is negative. That is why a negative is there outside to compensate for that opposite nature of these two strains. Okay, okay. It is basically a material property, a elastic property. It cannot be, although there are materials which are having negative, but the assumption that we are considering, so it is not negative, right? Although there are materials which are having negative Poisson ratio also these days, right? But generally we talk about metals which are nearly isotropic. Okay. So for an isotropic material, the Poisson ratio cannot be negative, right? It cannot be less than 0. Okay. So the Poisson ratio is given as minus of lateral strain to longitudinal strain. And minus is there because the lateral and longitudinal are generally having the opposite tendency. Understood? Right? Now let's try one question here. Okay. Very interesting. Okay, let's try. I'm very sure we can do it. Please go for it. Let's try it. Please do it. I'm very sure we can do. Please do. Please do. Any answers? Very simple question. The live students can answer me. Please try and answer. Now, see, very simple. So it says a metallic rod of 500 length. A metallic rod is there whose length is 500 Okay, the length is 500 right? the length is 500 mm and the diameter is 50 mm. And the diameter is 50 mm. Okay. When subjected to a tensile force of 100 kilonewtons, so it experiences an increase in length of zero point 0.5 meter. It experiences an increase in length of zero point 0.5 mm and length is 500 mm. Okay. And the dia is reduced. So dia is reduced. That means delta D is minus 0.15. Delta D is minus 0.15 mm and D is 50 mm and D is 50 mm, right? Now in this condition, what is going to be? In this condition, what is going to be the mu? So mu is minus of lateral to the longitudinal stress. So mu is minus of lateral is what? So minus delta D, okay, minus delta D by D upon delta L by L, that is zero point 0.5 upon 500. Okay. Now from here we can obviously calculate it. So see how much we are getting. So it seems to me, so it is 0.015 upon 50 and zero point 0.5 upon 500. So I think we are getting zero point 0.3, right? Okay, see this will become 10. So this is going to become 0.15. So 0.15 divided by zero point 0.5 will become plus and this is going to be zero point 0.3. Understood guys? Yes or no? Any issue? Yeah. So see how to calculate the Poisson ratio. I hope that is also clear. Okay. Now let's try one more question. So this is a little complicated, a little complicated, and may require the use of calculator. But see why I'm going to give you this question here. So I'm going to give you this question here so that you see you will be able to understand it how we can use these formulas, right? Okay, let's try this one. See, sometimes questions are given so that we can explain you the concept well, right? I can give you many easy questions. You can be doing it like this, but see, I want you to do some tricky questions so that you'll be developing some aptitude or some strength in this particular part of physics as well. Now, please do it. I'm very sure we can do. Please do it, guys. Please do it. Please do. I'm very sure we can do it. No problem at all. Please go for it, guys. Please try doing it. I'm very sure we can do it if we try to. Any answers? Any approach, like how we can approach this question? Can anyone please try to tell me that how can we approach it? Please try. Please try, guys. Please try. I'm very sure we can do it. Any answer? Any answer? Let's see how we can do it. Please try to. I'm very sure we can do. No problem at all, guys. Now it says a bar of diameter 30 mm, it is changed subjected to an axial load of 5000 kilonewton. Its diameter is changed to 29.891 mm. Find the Poisson ratio in Young's modulus if modulus of rigidity G is okay. So this is okay. G is 70 GP. It is given. Right. Now see how we can try this question. Now come. See if you understood all this concept, so see what I'm trying to tell you, because ultimately in the examination, what we are going to get, we are going to get the questions only, no? So see, when you see the formula, nobody is going to ask you this, that from where this formula, what is the interpretation of this. Although I have told you all this, but ultimately, what is the thing that is going to be actually useful for you is that in a question, how can you use all these formulas, right? That's all. Okay, nothing more is going to help you anyway, right? So see, P and we have L. So L is not given. Okay, let go of it. What is the diameter? So diameter is given as 30 mm. Okay, diameter is what? It is 30 mm. So we are having P and we are having some diameter. So this is of circular cross section. This is one of, this must be a circular cross section. So a bar of 30 diameter is subjected to an axial load of 5,000 kilonewton. Its diameter is changed to this. Find the Poisson ratio and Young's modulus, and one equation is given. So E is equal to 2G 1 plus V. I said, what is this relation? Actually, say for isotropic material, you can relate all these elastic constants. I'll give you all these relation. Although in this question it is mentioned only, so we can right away use it. Okay, so now in this equation we have the G. So E is equal to 2 into 70. That is 140. 1 plus mu. Right? Let's call it equation number 1. This is your equation number 1. So now in this equation, how many variables we have? Sir, we have 2 variables. Okay, so this is very calculative question. And you see, as I said, I am telling you this question, we are doing this question just for the purpose of understanding. Okay, we are doing it to understand the concept in a better way. Use of these formulas, how we can use all these formulas that we have learned in a better way. That is why we are doing. Okay. Now E is equal to 140 1 plus mu. So when E is equal to 140 1 plus mu, so let's call it equation number 1. Now we need one more equation. Now how we can do it? So stress is proportional to strain, right? So can we write stress is E times the strain? Okay. Now what is the stress? Sir? It is P upon A, and this is E times epsilon. But sir, we have no information about the epsilon. Sir, it is given the diameter and change of the diameter. That is the lateral strain. That is not your longitudinal strain. In this, Hooke's law relates the normal stress and longitudinal strain. Remember, okay? Longitudinal stress, normal stress and longitudinal strain. So this is P upon A, this is P upon A. So P is 5,000 kilonewton. 5,000 kilonewton. So 10 to the power 3 divided by area, that is pi by 430 square into Young's modulus we need to find, and this we don't know. Okay, so now let's do one thing. So what is the information we have? We know that mu is equal to minus of lateral by longitudinal strain. Right. But do we have the lateral strain? Yes, sir. It is final diameter minus original diameter upon original diameter. Change in diameter. Now, so final diameter is given 29.891. 29.891 minus 30 upon 30. 29.891 minus 30 upon 30. Now, from this equation, can we also write this is minus of lateral by longitudinal? Right? Please answer me. Right or wrong? Right? So from here, what we are getting? See, so longitudinal strain, sorry, this must be mu. Okay. So longitudinal strain is minus of lateral. So when we calculate it, we are getting minus of 0.109 upon 30. So this is going to be 0.109 by 30, right? That is your, sorry, this is your lateral strain, right? This is your lateral strain. So we have the lateral strain as 0.109 by 30, right? I hope it is fine to everyone. 0.109 by 30, no problem, sir. Now see, what is the longitudinal strain? So so what is the, so see, already I have taken minus here, or we can directly see, just So we can directly find out the longitudinal strain. So this is minus, I'm putting it like this. So minus upon mu. So what is the longitudinal strain? It will become 0.109 by 30 mu. 0.109 by 30 mu. Right? So let's suppose this is equation number 2. This is your equation number 2. So we are having equation 1, equation 2. Right? Now the question is sorted, isn't it? Sir, we are having two equations between E and mu. And we very well know that between any two variables, when we have two relations, two equations, we can easily solve those equations to get the value of those parameters or the variables. So from here, can we get E and mu? Yes, sir. So when you're solving, see, solving is not the issue. See, without calculator, it is going to be very difficult. Okay, but sir, why then you are giving us this question? Because I want you to give an insight that how we can use this equation, how can we manipulate all these equations of, the properties of solids and can use it. Okay, so when you solve it, you will be getting mu is equal to somewhere near 0.007, and this is will be somewhere near 154 GPa. I hope it is fine to everyone, right? Okay. Please answer me, guys. Right or wrong? Yeah. So let's try one more question. Come, let's do it. Let's try it. Come on, let's do it. Come on, very simple. Please try it. Let's try it. I'm very sure we can do. Please think how we can do it. Please go for it, guys. I'm very sure we can do if we try to. Very, very simple, straightway question. Please try to do it. Please do it. Any answer? Any live students? It seems to me that some of you are attempting. Can you answer me? See, if it may get wrong, but you can try at least to answer. Please do that. Please try to answer. So see, very simple. It says there is a steel bar. So whenever see they use this kind of a word that this is a bar, so we are having a steel bar which is 40 cross 40. So this is 40 cross 40 and it is subjected to axial compressive load, that is 200 kilonewton. If the length of the bar is 2 meter, let's suppose this is 2 meter, okay, and Young's modulus is 200 GPa. E is 200 GPa, right? So how we can deal with it? Now please understand this. So see, we have only one formula. Remember that we have only one formula. So delta is equal to PL upon A. So delta being PL upon A, so P is the minus 200 into 10 to the power 3. Okay, L is 2 meter, that is 2000 upon area. Area is 40 cross 40 into Young's modulus, that is 200 into 10 to the power 3. So from here we'll be getting 1.25 mm. Okay. Please tell me if it is fine to everyone or not. Yeah. So this is going to be A option. Understood? Yeah. Okay. Now let's do one more question. So let's suppose we are having, so find, so this is a neat question. Elongation of a steel bar. Find the elongation of a steel bar 1 meter long, 1 meter long and 1.5 centimeter square, 1.5 centimeter square cross sectional area, cross sectional area, cross sectional area when subjected to when subjected to a pull of 1.5 into 10 to the power 1.5 into 10 to the power 4 Newton. E is equal to 2 into 10 to the power 11 Newton per meter square. Okay, please try it now. Please go for it. I'm very sure if we try to, we can definitely do it. Please go again. Go for it. Please go for it. I'm very sure we can do. Please do it. Please answer it. Shubham, hello, very good evening. How are you doing, my dear? My name is Dr. Shankar Sir. So, my dear, in this session, we are talking about the properties of solid. Right. So, we have been speaking about the Hooke's law. Now, we are seeing that how we can deal with the normal stress and the longitudinal strain part. How can we take care of the Poisson ratio and all these things. So, we have spoken about this. And in this order, we are doing this question. I hope your preparation is going fine. Can you please try this question? So see, I have started the 11 physics part 2. Okay, and we are taking the bulk properties of bulk materials. Afterwards, I'll take properties of fluid, and along with the Newton law of motion also we are going to start with. Please do. Any answers? Please do. So let me try. It's a very, very simple question. So fine. So we have done so, good questions. I don't feel that you are going to have any problem in this. Okay. So find elongation of a steel bar 1 meter long and 1.5 centimeter square cross sectional area when subjected to a pull of 1.5 into 10 to the power 4 Newton. So this is 1.5 into 10 to the power 4, 10 to the power 4 Newton. Okay, 1.5 into 10 to the power 4 Newton. And this is the area is given and length is given. So this is 1 meter. Right. Now see, what is the elongation? So elongation is PL upon A. Right. So what is going to be the elongation? This is going to be what is P? P is 1.5 into 10 to the power 4. Right. What is this L? L is 1 meter, that is 1000. Okay. Upon area. Area is 1.5 and E is 2 into 10 to the power 11. So from here we can get the delta. So when we solve it, so see what we are getting. So we are getting C. So 10 to the power 11. So 4 and 7. And this is what we are getting in. So see, check the unit. Okay, so see. So see, this is 1.5 centimeter square. So if I convert it into mm, I'll be getting, so see, this is in Newton, length I have put in mm, so area I need to convert in mm. So it will be multiplied with 100. Okay, and E, it is 2 into 10 to the power 11. So that is, how many zeros will be reduced? So it will become 2 into, I have to convert it into mm. So 10 to the power 5, right? Now let's check the zeros. So 4, 3, 7. 5 to 7. So 1.5, 1.5 will be cancelled out. So 1 by 2, that is 0.5 mm. Okay. So what is the elongation? It is 0.5 mm in this case. I hope it is fine to everyone. Okay. Okay. So guys, this is how you can deal with the Hooke's law when we talk about the normal stress, longitudinal strain. So guys, this see in this session what we did, we seen the normal stress, we seen the longitudinal strain, we see the lateral strain, we see the Poisson ratio. Okay. So I'll be coming up with one more session. I'll be coming up with few more sessions on this. And in the next session, probably we are going to see the relationship between the elastic constants and how these elastic constants govern the elastic properties of the solid. And we'll be also talking about the stress strain curve. Okay. And then for the strain energy, thermal stresses. So everything I'm going to deal. Okay, so with this, thank you very much. Have a good day. And don't forget to subscribe.